So 8.5 part 2. Remember, this will be the same PDF you used for the first homework assignment. It'll say 5.4 at the top. So we just started talking about at the very end of the section a different notation for vectors that doesn't involve drawing. It involves these angle brackets, and we put two numbers between them with a comma. These indicate your horizontal and your vertical components. Doesn't tell you where to start, but generally if you want to draw a vector, we start from the origin. So in order for these two vectors to be the same, let me draw an example. Okay. If I drew this, and then I drew this, do you think those two vectors are the same?
Yeah.
Yes. Being the same doesn't mean they're in the same spot. Like if I said to you, are these two coordinates the same? And I wrote down two ordered pairs. Well, for two coordinates to be the same, they need to be in the exact same spot. But vectors don't. All that it means for one vector to equal another vector is that the horizontal components of the vector and the vertical components are the same. Doesn't matter if you started at the origin or you started somewhere else. Another way to think of it would be is if you had two vectors like this and you dragged them so they had the same initial point, would they look exactly the same? And the answer there is yes. So as long as they have the same initial and terminal point, when you drag them together like that, then yeah, they're the same. Another way to think of it is they each have the same magnitude and they have the same direction. As long as they have the same magnitude and direction, they are the same vector. So any question on what it means for two vectors to equal each other?
Is that what you're saying? They're the same when they're in the exact same spot?
If they started in the same spot, then yeah, they would look the same. But they can be in different spots, and those are considered equal. Okay, so the last notation we're going to look at, and this is the notation we're going to use pretty much the rest of the week, is called unit vector notation. So it's going to rely on what we call unit vectors, and we talked about that last time. What makes something a unit vector? Right, it has a vector with a magnitude of 1. Well, what we're going to do is we're going to define two special unit vectors. Kind of like, in math when you have a constant, like pi, right? That Greek letter in math is used to represent a number, and you never use that letter for anything else because it means 3.13. Well, we're going to do the same thing here. We're going to define a special vector using the name I, so you can no longer use an I to represent the name of a vector. Okay, I is something special. I is a unit vector that points to the right. So I is going to be defined as a vector that points one unit long, and it points to the right. There's a picture of what I looks like. It's 1 unit long, points right. We're going to define one other special vector, and that's going to be j. J is going to be a unit vector that points up. So j is a unit vector that points up. There's a picture of j right there. So any questions on what I and j are? Now, what we're going to do is we're going to think of I and j as like building blocks, like pieces we can stack together to make vectors. And if you think of building a vector piece by piece with i's and j's stacked together, that's going to give you the last notation that we use. So let me show you an example. Okay, so let's see if we can build the vector 3, 4 out of i's and j's. It doesn't matter where we start. We're just drawing a vector. So if you wanted to draw the vector 3, 4, you could start there, and it would end up right here. Now to figure out how to build it, I'm going to stack i's and j's together until I end up starting at my initial and get to my terminal. How many i's would I need to start moving in the direction towards my terminal point? 3. So I'm going to take and make 3 copies. Yeah, it's probably easier if I just draw it. But there's 1 I, 2 i's, 3 i's. So what we just built right there is this. 3 I. I'm going to put some more. So we have 3 I. And then I'm just going to draw them. How many j's would I need? Yeah, I would need this one, 2, 3, and 4. 4 j. That's called unit vector notation. 3i plus 4j.
Can you just look at the 3, 4? That would give you your answer.
Yeah. That's all you really have to do. Right, but that's where this I and j are coming from. I want you to think of them as you are really adding them together. In this case, you added 7 vectors together, kind of like in the homework, but you never had to add 7 of them. Maybe I think we did like 4 or 5 on that, the last one I did. But here you're adding 7 vectors together, and then you connect where you started to where you stopped. And that produces the vector that we wanted.
Yeah, but we already use I for imaginary numbers. Why can't they just choose like T? No. What's something? You find a letter.
Yeah, I don't know why.
Letters. Like I'm sure it's going like physics.
Remember, these are bold, so you would see them as bold, so that would differentiate it from an I.
That's lame.
But yeah, they use I. Okay, so 3i plus 4j. And if we did it in 3D, then we'd have a k on it. So then we could do that as well. Was there any question on how I got that notation from that notation? Okay, so let's look at a few formulas for working with vectors. I'm going to show the formulas, I think, using the notation we learned on Monday. But we can use this new notation when we do some problems. We'll practice both. So for what I'm about to show you, v and w are going to represent vectors. Each vector has its own horizontal and vertical component. And alpha is a scalar. Okay, remember, we talked about what scalars do. Make them longer, shorter, flip the direction 180 degrees. So what we're going to look at is basically everything that we did on Monday, but now we're not going to draw it. I'm going to show you how to add these vectors without drawing, subtract them, and scale them. But no drawing. If you want to add these two vectors together, and you were drawing them, well, if that was the first one, and that was the second one, you'd have to use a piece of graph paper, position the vectors so that the end of one and the beginning of the other line up, and then you'd connect to that adding. Well, if you want to do the same thing, but just do it numerically, all you have to do is add the horizontal components of each vector, and that gives you the horizontal of the new one. Add the vertical components of each vector, And that gives you the vertical component of the one. And subtraction is the same idea. Remember, with subtraction, though, what we'd have to do is visually, the one we're subtracting, we'd have to flip it around and think of it as adding the opposite. But now we don't have to do that because we're not drawing. All we're going to do is subtract the horizontals and then subtract the verticals. And now the next thing is going to be scaling. If we wanted to scale a vector, let's say this was vector v, and I wanted to make that 3v, how would I do it visually? Yeah?
You add 2 more.
Yeah, I have to add 2 more, so there's 3v. Well, when you want to do it without drawing it, you can think of alpha, which is a scalar. It could be a 3, a 2, a negative number, it could be anything. Think of the scalar as being distributed to each component of the vector. So if your vector was x1, y1, and you wanted to double it, well then just double each number in the vector. Double each component. So it's like distributed property. And now if I was going to extend this formula to 3D, I'd have this. We're not going to worry about that part today because this part's always going to be a 0. When you do 2D, the 3D part is just 0. But if you were going to scale a vector in 3D, you multiply the x component by your scalar, the y component, and the z component. All 3 components get scaled. And then we have that symbol. Someone remind me, what is that?
Isn't that, is that the absolute value? No, sorry.
Magnitude.
I was thinking of the this velocity.
And what's the magnitude visually? Like if you're looking at that arrow in red, what's its? I'm not looking for a number. I'm looking for you to describe. It's the length of the arrow. How would you get the length of that arrow in red? Yeah, you just do Pythagorean theorem. 3, that's 4. So the magnitude of that vector is 5. So to find the magnitude, take the horizontal component and square it. Take the vertical component, square it. Add them up and take the square root. And that's exactly what this formula is saying to do. Horizontal component squared plus vertical component squared. Add them up and take the square root.
Considering we'll probably get there, but how do you find that for 3D?
For 3D, you just basically go like this. That's the Pythagorean theorem in 3D. Square the x, square the y, square the z, add them all up and take the square root. Like I said, it's this easy to do in 3D. You just add that part onto the end of every formula we've done. I didn't show you for the adding and subtracting here, but you just put like a z1 plus z2 right on the end of it, or a z1 minus z2. Yeah, this part for today, that's going to be a 0, so I'm not going to write it down. Okay, well, let's try this. So we got a couple of vectors. I've written them both in unit vector form and the notation we learned on Monday. And the first thing I want us to do is add them up. Okay. Let's write the answer as ij first, and then we'll write it the other way. Can anybody tell me what you'd get if you add those 2 vectors together? Yeah.
5i minus j.
Yep, 5i minus j. And can you give that to me in this notation?
5 minus 1. 5 common negative 1.
Same thing. You're not going to have to write both ways for a test question, but that's how you do both. Questions on that?
Sorry, what? Is that just an example of how to write it?
Mm-hmm.
Like we put 1 together.
How about, let's try subtracting. What would you get if you subtract V and W? Okay.
Negative I plus 7J.
Yep. Negative I plus 7J. Which if we wrote it in the other notation would be
Negative 1 comma 7.
Yep, negative 1, comma 7. So adding and subtracting, you need two vectors to do it. But when we do scaling, you only need one. Okay, so W is not part of this problem at all. So let's go back up, look at V. And the directions here are saying to scale V by a factor of 3. So what would this V, what would 3V come out to? 6I plus 9J.
You scale both at the same time.
What do you mean?
Both V and W.
Oh, we could have done it, yeah, it'd be another example, but.
Like 3V plus 2W.
Oh yeah, so you could have a more complicated problem, so then you want to do the 3V first, the 2W first, and then add them together. Yep, you could do that. And the last one, again, magnitude. That type of operation takes a single vector. You don't need two. You could do two. Like you could definitely have this. Think of that as like order of operations. You're going to do V plus W first, and then when you get the answer to that, find the length of it.
Sorry, what was it you used?
So what's going to be my formula to find the magnitude of V if the components are 2 and 3?
2 squared plus 3 squared, take the root.
2 squared plus 3 squared, take the square root. You're really just finding the length of the hypotenuse. So that's going to be the square root of 13. If they want a decimal, you could write it. If they want it exact, just leave it like that. Any question on that? So with the exception of finding magnitude, example A, B, and C, that's everything we pretty much did on Monday. Add, subtract, and scale. That's most of what we did on Monday. But it's a lot faster if you don't have to draw it. Okay, so reminder just what a unit vector is. It means that it has a length of 1. So here's an example of like a vector in black. And then maybe this is a unit vector. What I'm going to be finding next is unit vectors given a vector. So if you're given a vector that's too long, I want to know what you would have to scale it by to shrink it down and make it exactly 1 unit. That's what I'm trying to find. Or if you have a vector that's too short, what would you have to stretch it by to make it exactly 1 unit? I still want it to point the same way. I just either want to stretch it or compress it to make sure it's exactly 1 unit long. So think about some examples. Let's say you had a vector that had a magnitude of 5. What would you scale it by to force it to be 1 unit long? 1/5. How about if you had a vector that was 8 units long? You'd scale it by 1/8. What if you had a vector that had a magnitude of 1/3? You'd scale it by 3. So now, what if you had a vector that had a magnitude of, I don't know, let's just say whatever number that is, that's the magnitude. What would you scale this by? Yeah, you always scale it by the reciprocal. So if your magnitude is a number, multiply it by the reciprocal, and that will turn it into a unit vector, which I think I have written down right here. Yeah. So 1 over the magnitude. That's the pattern. So let's say you had you had a vector called v. If you wanted to take this vector and force it to be a unit vector, you would find how long it is, and that's what you would scale it by as a reciprocal. So if you found the length of it, took the reciprocal, and multiplied your vector by the reciprocal, it would force it to be 1 unit long. That's the pattern I was trying to show you. And if you want to put all this together, if you're scaling a vector by 1 over its magnitude, it's really like you're just dividing the vector by its length. So dividing a vector by its magnitude will convert it into a unit vector. If it already was a unit vector and you do this, then you'd be scaling by 1. Nothing would change. Any question on that formula? Sometimes if I jump right to this, people get a little confused, like why do you have a magnitude in the bottom? But it's because when you multiply by a reciprocal, it forces it to be 1. That's why it's in the bottom. Okay, so let's find the unit vector for 3I minus 4j. If it's already a unit vector, then we're done. If it's not, then we need to either shrink it or stretch it to make it exactly 1 unit. But how are we going to know if this is a unit vector? What do I need to find?
You need to find the length of the vector.
I need to find the length of it. That's the only way I'm going to know if it's a unit vector. So how do I set up for the length of 3I minus 4j? So 3 squared, yep.
4 squared.
Plus, what's my vertical component?
Negative 4 squared.
Yeah. So what does that give me for a length of v? 5. So is that a unit vector?
No, this is a unit vector.
It has to be 1. So now, what am I going to scale the vector by?
1/5.
1 over its magnitude. 1/5. So what is 1/5 v? Let's do this notation.
3/5 I minus 4/5 j.
3/5 I minus 4/5 j. There you go. So that's a unit vector. It points exactly the same way as the original one. We've just scaled it by 1/5 the size. Any question on that? Now, we don't really focus on doing unit vectors a lot in 3D, but you'd do the same thing. If you had to do it in 3D, well, find the length of it in 3D. So it just has one more thing you have to add and square. And then use the same formula. You could scale, you'd have something in 3D. So if I wanted to force that to be a unit vector, the length of it is 4 plus 9 plus 25. And what's 4 plus 9 plus 25?
38.
So it's not a nice number. But if you wanted to turn that into a unit vector, it's 38 units long. Okay, well, square root of 38 units. To turn it into a unit vector, you'd have to scale it by 1 over the square root of 38. But if you multiplied that out, it would make that a unit vector.
Sorry.
Since the thing was 38, you have to multiply it by 1 over 38.
All right.
Velocity.
So the two applications that we're going to look at. We're going to do a little more with velocity vectors tomorrow. Today's is going to be pretty simple for this one. Remember what velocity is. It shows you the speed and the direction of an object. We looked at those airplanes on Monday. Now, we're going to think of all the problems we're doing as two-dimensional. Okay, we're not really going to get into 3D problems. So let's say that somebody was standing like right here, and they throw an object like that. Now, when you throw an object, obviously with gravity, it's gonna curve back down. But to keep what we're doing simple, let's pretend it was like in outer space, and the object is projected in that direction. If you think of this two-dimensionally, what direction is this object moving in if it's following that path of it?
Right.
Northeast.
Right, north and east, right? It's going right and up. So it's traveling two-dimensional. It's traveling to the right, but it's also traveling up at the same time. When we talk about a 2D vector, it has components to it. It has a horizontal component, and it has a vertical component. So when we want to write something as a velocity vector, we need to break the vector down into its components. How much horizontal speed does it have, and how much vertical speed does it have? Because those are two different things. If I throw something straight up like that, it had no horizontal speed, 0. Everything was vertical. But if it's on an angle, it's some combination of the two, right? And we can figure it out. So how do you think we would describe, if you're looking at this diagram, the direction that arrow is pointing?
Like guessing numbers or
Well, I'm thinking of something, if you knew in that diagram, it would tell you exactly how it's pointing. Yeah?
The degrees from the initial.
Yeah, if we knew an angle. Yeah, we're going to know an angle from the horizontal. So, I'm trying to think. I just want to make sure I use the right Greek letter. It doesn't really matter. Okay, I use alpha. So let's use alpha. Alpha is the angle that the object is thrown at. That's one thing that's going to affect it. That's the direction. Now, the magnitude of this arrow represents what? If this is a velocity vector.
or like the speed.
Well, yeah, the magnitude is represented by the length,
Yes, I was thinking about that as part.
which is the speed. So those are the two things that you need to know to write something as a velocity vector. How fast is it going? What angle is it going at? And then we can do this. We can figure out the horizontal component of the vector, and we can figure out the vertical component. So we have to break the vector down into its components. All right, let's call this side x. Let's call this side y. How could we find x if we know the angle and we have that vector?
You do side. Oh, and then you don't know x.
Yeah, it would be cosine. The cosine of what?
But we have all the angles.
Yes, you're going to be given this angle in the problem.
Yeah, so then we have all the
Yeah, there's only one that you need. Yeah.
Okay.
So you're only going to need this one, and they'll give that to you.
So then it'd be side to side. No.
So we want to use cosine somehow.
It'd be x over the
Anyone know how we would use cosine?
Cosine alpha.
Cosine alpha. Yep.
X equals X over the vector.
X over. Now, what about the vector? Because we don't want to put the vector in the bottom. We want the magnitude of the vector. Because this side is always about lengths. I just let X represent the length of this side. So we want cosine alpha times equals X over the magnitude. That's the length of the hypotenuse, if you want to think of it that way. Now, how would you get X by itself? Multiply both sides by the magnitude. So the horizontal component of the vector is the magnitude, which is the speed that the object is traveling, times the cosine of the angle the object is traveling at. Now we need to do the same thing for the vertical. What trig function is going to allow us to find the vertical component? So we got sine. Okay, sine of alpha is going to equal what? Right. Opposite over the length of the hypotenuse. And what would y be when you get it by itself?
Magnitude sine alpha.
The magnitude sine alpha. So when we want to write a vector, remember how you do it? That's a 2D vector. Just substitute in the two things. So the horizontal component is magnitude v cosine alpha, and the vertical component is magnitude v sine alpha. So that's using the notation we learned on Monday. But if you want to use the notation that we just learned today as a unit vector, well, there's your horizontal, so magnitude v cosine alpha with an I, and then plus magnitude v sine alpha, and that would be my J. So both of these are the formulas for velocity vectors. But it does depend on knowing two things. How fast was the object thrown at or projected at? So this is the speed, and this is the angle. Like if you throw something at a 90-degree angle, that essentially means you threw it straight up. It's not going to travel forward at all, which means one of these components is going to turn into 0. And that's the same angle. Okay, so any question on the formula for a velocity vector? We're probably going to use the bottom one. The top one. So this is where the trig part comes in. Okay, breaking down a vector into its really two sides of the triangle. And then I think I wrote the same thing somewhere else. Yeah, right. It's the same. So we don't do that again. Let's look at this. So it says we're going to throw an object at 50 miles an hour at an angle of 30 degrees. Find the velocity vector. Write your answer in unit vector form. And then explain the meaning of the horizontal and the vertical component in relation to this problem. What the numbers actually mean. Okay, so what's the speed? 50 miles per hour. Is that my angle or is that my magnitude? That's my magnitude. Magnitude of V times the cosine of, what's my angle? 30. And And which component is that? 50 cosine 30? That's the I, the horizontal. And what's going to be my expression for the vertical component?
Same thing with the sine instead.
The same thing with sine.
J.
90 degrees. Okay. Okay, so do that out, and that's the answer. So we've got 50 cosine 30. That's 43.3i plus 50 sine 30, 25j. So there's the velocity vector that represents throwing an object at 50 miles an hour at an angle of 30 degrees. Now, what does that number mean? Like in this real life problem, what is 43.3? How would that be observed if you were watching the situation? What would be 43.3? Yes?
It would go, the object would have flew or been thrown 43.3 minutes way more.
Remember, this is a velocity vector, so these have something to do with speeds.
Is it the horizontal speed that it's thrown?
This is the horizontal speed of the object, yes. So like if you were throwing an object at 50 miles an hour at an angle of 30 degrees, and there was a sensor on the wall that could measure how fast it hits it, it's not going to hit the wall at 50 miles an hour because you didn't throw it straight at the wall. You threw it at an angle. So some of your power went into throwing it up rather than throwing it forward. So it would hit the wall at 43.3 miles an hour. That's how fast it's traveling at the wall. The 25, what would that be?
Would that be the vertical speed?
That's the vertical speed. So, and in theory, that's the maximum vertical speed because it's going to be going the fastest vertically the second it leaves your hand. Once it leaves your hand, gravity's slowing it down the whole time. So if you were like up above this person throwing this object with a radar gun and you pointed it down and you could get the speed the second that it left their hand, it would say that the ball is coming up at you at 25 miles an hour. Does that make sense? Okay. Horizontal speed from physics, that would never change if you discount air resistance. It's going to be traveling 43.3 the whole time because gravity has no effect on horizontal speed. The only thing that would affect that is air resistance. Any question on that one? Okay, so out of the two applications, that's the easy one for today, figuring out the vertical and horizontal components really of a vector. Okay, so the last one we're going to look at has to do with what's called static equilibrium. The idea of static equilibrium means you have a situation where nothing is moving. Everything is balanced. Right? So like if you look at the stand that holds my book, it's not moving. Right? It's staying perfectly still. Even though it has weight to it, it's pushing down on the ground, but the ground's pushing back. So it's holding it still. So the idea is if something's in static equilibrium, it means that it's not moving. And if something's not moving, it means all the forces are balanced. And if you want to think two-dimensionally about that, that means up and down forces are equivalent, and left and right forces are equivalent. If the forces didn't balance each other out, then all of a sudden it would start moving, because one force would be stronger than the other. So that's what static equilibrium means. You have an object that's staying still because all the forces acting on it are balanced. And by all, I mean verticals and horizontals, two-dimensionally. Okay. Any question on what that means? Okay, so here's our. So we've got a weight being suspended from two cables, and I want to find the tension in each cable. Now, just to kind of get something out of the way right away and clear up, you can have more tension in the cable than you have weight pulling on it. And think of imagine you had a huge tug of war rope, like a real big rope. Maybe that rope weighs like 50 pounds, all the rope. But if you put 30 people pulling on each side, could you have more tension in that rope than like 50 pounds of tension?
Yeah.
Yeah. You can have way more than the weight of the object, because not only is it the weight of the object, but it's the amount of horizontal pulling on it too that causes tension. So the only way that you could have equal tension in each rope would be like if it was like the lights. You have perfectly vertical attachments to your weight, and they're all equally spaced. I know that last one, but pretend like they were all equally spaced. Then you could divide the total weight of the lights by how many vertical supports there are, and they're all supporting the same amount. But you start putting things on angles, and it gets more complicated. So that's what we want to figure out. Okay, so first thing before we even look at the diagram, I kind of just want to write down the general idea of what's happening. This object is not moving. I want to think of this object as only being able to move in two different ways, left and right, and up and down. It can't move in and out. That'd be 3D. So if it's not moving, what did we say earlier that means? It's in static equilibrium, which means all forces are going to add up to 0, right? And specifically, what two directions do we have to think about? Right. So let's start with the horizontal. If it's not moving horizontally, then I know that the force pulling it left must be the same as what? Right. These are the same. We have to start putting some numbers in here and thinking more about that. But that's kind of the concept we're going to start with. So left equals right. And what else do we know? The force up. That's not a nice way to write that. Let me think of something better. The force up equals, well, we know the force down. What's the force down? We don't have to guess what force down is.
It's gravity.
It's the 1,200 pounds. That's the only number we can put in really easily. Any question on that concept? Up and down is equal to each other, and left and right is equal. Okay, now I want to start drawing on this a little bit. Let's call this cable, let's make this the tension in cable 1, and this will be the tension in cable 2. Which way is cable 2 pulling on the weight? Up, and which way? And right. And the way you feel like, wait, why is it pulling to the right? Well, think about it. If you cut cable 1, what would happen? All of a sudden it would swing to the right. Why would it swing to the right? Because cable 2 is pulling it to the right. So this cable is pulling up and right. And what about cable 1? Up and left. Because if you cut cable 2, all of a sudden it would swing to the left because cable 1 is pulling left. Is there any question on that? Now what we want to do is think about breaking these vectors down into their components. Because I need to think about it not as pulling like northwest and northeast. I need to think about it as left and right and up and down. So I'm going to break these vectors up. So the way we're going to do that is we're going to put in a horizontal, just like that. And then we're going to draw 2 verticals, just like that. So that's a 90, that's a 90. So let's do it like this. That's the horizontal component of cable 1. That's the horizontal component of cable 2. That's the vertical component of cable 1. And that's the vertical component of cable 2. Any question on that? So what we want to do now is let's give names to these 4 things. So we don't have to say green arrow 1, green arrow 2. That's too confusing. What letter do we usually use to label horizontals? X's. So let's call this, I wanted it to be black, but that's fine. So let's call that one X1. And what would we call that one over there? Yep. We'll call this one X2. And what would we call the green one? Yeah, the green one on the left, I should say, is Y1. And on the right? Y2. So now let's substitute the labels X1, Y1, X2, Y2 into these equations and try to start to get something that is connecting more with this diagram and not just conceptual. Force left. How did we label force left here? Yep. So what I can do is go like this and say this is going to turn into X1 equals, what's the force right? X2. And then this one, force up equals 1200. Okay. What are the up forces? Yeah?
Y1 plus Y2.
Y1 plus Y2 because they're working together. That's why you add them. That's an upward force, and that's an upward force. So Y1 plus Y2. And we know that those 2 upward forces working together are supporting a total of 1,200 pounds. Okay, so that's kind of the second stage of our equations, taking them more from just a concept to now actual labels in our diagram. Any question on that? Now, the third step is to actually get all these in terms of angles and sines and cosines. So what we're going to do now is figure out 4 things, x1, y1, x2, y2, all in terms of sines and cosines. So we need to label some angles here. Let's use this one and this one. What's this angle? 30. That's 30. All kinds of ways to figure it out. Parallel lines and a transversal, or use 60 and then that has to be 30. However you want to do it. That's 30. And this one?
45.
That's a 45. Okay, so let's start with x1. I'm going to move my T1 label right here so you remember that's the hypotenuse. And I'm going to move my T2 label there so you remember that's the hypotenuse. Okay. What trig function could we use to get x1 that would involve this angle and the tension in cable 1? Cosine. So let's write that down. Cosine of what? 30 equals x1 over t1. And my goal is to get a formula for x1 that I can then substitute in. So what is x1?
Cosine
T1.
So yeah, I'm just going to say t1 cosine 30. Okay, there's x1. Now let's do x2. I want to use this angle. I want to find x2, and I want to use tension 2. What trig function would I use for that?
The sine 45.
That'd be cosine.
Be cosine again. Yeah, we're going to do sine in a minute, though. Well, let's do cosine again. Cosine 45 would equal what? x2 over t2. T2. So that means x2 equals
T2 cosine 40.
Yeah. So the pattern is the horizontal is always hypotenuse cosine angle, And the vertical is always hypotenuse sine angle, without going through the whole thing. So y1 is going to be t1 sine 30 degrees. So now we have that. And what about y2?
T1 sine 45. T2 sine 45.
T2 sine 45. You can go through and figure it out just like we did the other one.
Wait, sorry, how did you get the one for y?
Oh, why? You just use sine instead of cosine.
Oh, okay. Never mind. Sine.
And now the physics part of this is done. That was really done at the first step. You wrote down the concepts of forces being balanced. The trig part of this is now done. That's where you broke the vectors into their components. Now, from here, it's really algebra 1. It's solving a system of equations. You need to take these equations and fill in what we have. So let's do x1 equals x2. So our first equation is t1 cosine 30 equals t2 cosine 45. And the second equation, y1 plus y2 equals 1200. So y1 plus, what's y2?
T2 sine 45.
And what does that equal? 1200. There's your system of equations. I think some people get confused because they see all these sines and cosines. Remember, these are just numbers. They're just numbers. So we want to solve this with substitution. That's the easiest way. Which equation here do you think is the easiest to get either the T1 or the T2 by itself? Which one?
Number 1.
Yeah, I'd say equation 1 because you can just do one thing. And you can choose if you want T1 or T2 alone.
Just divide those sine.
Sure, if you want to get T1 alone. So T1 equals T2 cosine 45 over, what did you say to divide by? Cosine 30. So we're going to come back to that because once we know T2, we just fill it in right here, and then we have T1. Okay, so what are we going to do? Actually, I'm going to do it more like this. What are we going to do with what's in that red box?
Substitute for T1.
We're going to substitute it for T1 right there. And we're going to start doing this out because we're going to have a lot of decimals here. Okay, so we're going to have T2 cosine 45 divided by cosine 30 times what?
Sine 30.
So I'm just going to put that in the top with everything else. Sine 30. Now I need all that done. I need to know what number that is. Okay, so we can do that. And then keep the rest of it the same. T2 sine 45 equals 1200. So now how many different variables are in that equation? Just one. So now we should be able to solve that for the tension in cable 2. So that's the cosine of 45 times the sine of 30 divided by cosine 30. Did I do everything? Cosine 45, sine 30 divided by cosine 30. That's 0.408. So 0.408 T2. Sine of 45, we've done that one before. What's that as a decimal?
Is a I can find it. The
Yeah, 707.
That looks like it.
Sine, oh, we already did it. It's 0.707 T2 equals 1200. Okay, what would we do now?
Add 0.707 to 0.48.
Yep, we need to add those up. What do you get when you add those two together? 1.115 T2. And my last step. Yep. And what do you get when you divide by 1.115? 1076.23. All right. So that's the amount of tension in cable 2. And now, what do we do with that?
Bring it back.
Yeah. Bring it back right there. And that would be the tension in cable 1. That's the easy part. Just plug all that in on your calculator and you can find what that is. So that's generally how a static equilibrium problem goes every time. There's never anything different than what we just did. Okay, but it all starts out with this concept of force left equals force right, and force up equals force down. And then we built our formulas from there. And if you start to get, a little bit better at it, you can really jump right to these final 4 equations, as long as you know the angles you're working with. That's all you need to know is the angles. Specifically, these 2. That's how I did it. Any question on that? So it takes a little practice with those, but I think there's one in the homework, so we can go over that tomorrow if you have a question. Okay, so homework for tonight. I think I'm going to change a couple questions. So it's 25 to 47 odd, 55, 57, and 66. 66 is the static equilibrium problem. So literally, you can just look at your notes, change the weight to 800, and change the angles to 35 and 50, and do the same thing. Right at